So get rid of that. Okay, everybody, just to get to where we've got to so far in the course. Last week I showed if you have a good look at the data, it strongly contradicts the capital asset pricing model. And the early success is pretty much a quirk from the short time period that FAMA looked at, which of course by the time 2004 came along, FAMA had to admit it wasn't in the market, the models simply didn't work. They've got a highly volatile market, and when you look at the dynamics, it follows what's called the power law process, which I showed you again a couple of weeks ago, that shows that any scale movement is possible in the market and certainly have happened. So what we've got therefore is a market that certainly has random components to it, but an essential part of it is not random. So there's some sort of pattern there, but of course those patterns are incredibly hard to work out. And one thesis that combines both those observations is called the Fractal Markets Hypothesis, which acknowledges that there's some very volatile pattern that's behind the market. So if you look at what CAPM was doing, one justification for developing CAPM in the first place was to try to explain why it was hard to make a profit out of the market. And CAPM will tell you that people who do technical analysis, looking at the ups and downs and charts and stuff like that, are wasting their time because there is no pattern. And their explanation for that was that they are fully informed, rational traders, market prices reflecting all the available information, and therefore the movements you saw were random. Therefore, the previous movements gave you no information about subsequent movements. Now, the failure of CAPM pretty much implies that that's not the case. Okay, it's not a random process. So there is a pattern, but it can still be incredibly hard to make money out of it, because the pattern is extremely hard to identify. And the Fractal Markets Hypothesis is an attempt to at least identify part of that pattern. So, anybody here know what a fractal is? As usual, the usual suspects know what I'm talking about. Most of you haven't heard of them before. So I'll give an explanation first of it. It's going to make about as much sense as the actual word itself. And that it's a self-similar pattern generated by a highly non-linear process. Now, what the hell am I talking about there? Well, let's go back and get a bit of history from what I showed you with the rational numbers earlier on, with that proof by contradiction that the square root of 2 is not a rational number. Rational numbers are numbers that are equal to the ratio of two integers. Now, irrational ones would like the square root of 2 and not. Fractals are similar in a way when you think in terms of landscapes, and they were first actually developed in economics by somebody whose work was ignored by economists. He then went across to geography, so most of the developments occurred in geography. There's also a predecessor who worked on the pattern of the water flows in the Nile a long, long time ago. So geography gave us a lot of what we know about fractals now. And thinking about landscapes and thinking about the shapes we use in mathematics to represent objects, could you describe landscapes using solids like cubes and rectangles and circles and spheres and so on? Now, clearly not, in one sense, because you look at Mount Everest and you say, well, does it look like a triangle? Well, only in the most extreme of ways, to say, yeah, it's got a point and a wide base, but it certainly isn't a single triangle, though you might notice this one over here. That's a pretty good triangular shape there. Okay, so you've got a yes and no answer to that. It's not like a single pure triangle, but it's like lots of small ones jumbled together. And Mandelbrot was the guy who invented the concept of fractals to describe objects like that. And he said that the real world geography we have doesn't look like pure Euclidean objects, but it does look like combinations of those. So is there a way of actually mapping between the integer Euclidean objects we know to the objects we see inside in the real world, and then is there some sort of relationship between the integer dimensions we use to describe squares, circles, triangles and so on, that we can actually use to apply to the actual landscape? Let's imagine you start with a simple triangle and then choose the midpoints of 3 of the sides of that triangle, and then move them around in the two-dimensional space that defines the triangle, and then create 4 new triangles by joining those new points with the vertices of the original triangle. So you've got a triangle with three vertices, of course. There is 3 midpoints. We then move them by a random amount to give ourselves 3 new points plus the 3 original points. And then you make up a shape that joins those original vertices with the new points we've added in, and from that you can create 4 triangles. 1, 2, 3, 4. Now that's looking slightly more like a mountain, in a sense, for irregular triangles. Keep on doing it, and the pattern you get does look like a mountain. So here's an illustration of that. And by the time you get to the 5th iteration, you've got something you can actually take seriously as a possible mountain. Now, how many of you played in computer games where you're in a virtual landscape? I mentioned lots of you. Come on, give me a bit of a show. Okay. Those landscapes are almost certainly generated using fractals. And just a series of taking an initial shape like that and then playing through 5 or 6 iterations, you've got something which looks convincingly like a real landscape. Now, Mandelbrot said, well, that raises a question now. We've gone from integer objects with an integer dimension like triangles and got something which looks like a mountain made out of triangles, but they're certainly not all the same size and regular. So he said, how do we map between the integer dimensions we have for those, and what can we call the dimension of a mountain? Now, of course, a Euclidean object like a line has got a dimension of 1, the square's got a dimension of 2, the sphere has a dimension of 3. So can you say the same thing about a picture of a mountain? Does it have 2 dimensions? Well, yeah, it's obviously 2-dimensional in one sense, but if you use triangles all of the same size, it wouldn't look like a mountain at all. So you say maybe it lies between a dimension of 1 and dimension of 2. Now let's look at how we actually define dimensions. If we look at a point, the abstraction mathematicians use to indicate a single location, that has a dimension of 0. And a line has a dimension of 1, a rectangle has 2. How can we work out a sensible measure for dimensions using the same sort of idea for a mountain? Well, I'll give you an example from a thing called the Cantor set, which is one of many what are called chaotic patterns, or this is actually quite chaotic, but it's a complex pattern. So you start, the way the Cantor object is built is you take a line and you chop out the middle third, which gives you 2 lines. And you do it again and again and again, and what you end up with, it looks like a simulation of Space Invaders. Okay? The end line has got many segments taken out. Now, is that 1-dimensional, 2-dimensional, or somewhere in between? There's lots of isolated points there. It could be 0-dimensional. So it lies between 0 and 1. Now, one of the measures that Mandelbrot, I think, was the person who developed, proposed to work this out was what he called the box counting dimension. And that says work out how many boxes you need to count the object and define it in such a way that Euclidean objects still get their 0, 1 and 2 and 3 dimensions, but these ones get something between the two. So the idea is how many boxes does it take to cover an object completely? And then apply the same thing to the Cantor set where you've got a line broken into lots of small segments. So it's a function of the number of boxes you need and the size of each box. So we're looking at the size of one side of a rectangle or one side of a square, that sort of thing. And the measure is the limit of the ratio of that, the log of the number of boxes divided by the log of 1 over the size of the box, measured either by the side of a rectangle or side of a square. Now, that looks a bit strange. Let's just try applying it to an isolated point and see what we get. Because you need 1 box. No matter how small the box is, it simply takes 1 box to cover it. And therefore, if you define the size of the box as eta can go towards 0, and therefore 1 over eta, which is part of the argument for the bottom line of that expression of the box dimension, goes to infinity. So there's your single point. A box of eta equal 1, eta equal a half, eta equal a quarter, keep on going as small as you like, you still cover it. So the box dimension value, the box counting dimension value for a single point is 0. It's the log of 1, which is 0 itself, divided by log of 1 over eta, which goes to infinity. You use smaller and smaller boxes. 0 divided by infinity, obviously 0. But of course, many points also have to come out the same way. So if you had, say, 4 points there rather than just 1, applied the same operation, well, rather than n being 1, n is now 4, but you get the same basic result because you're dividing by the log of 4, which is 0.7. Actually, that must be I'm using the log. That's using the log base 10 there rather than log n. I better change that for the later lectures. That tends to that is 0.7 in base 10, and you divide that by the log of 1 over in 0. Again, you're still going to get 0. So you get the right answer for a single point. You get it for a line as well. There's your box, 1 unit long, 1 box. Try 2 boxes. You've got 2 boxes, each which are now half in a unit long. So n is a function of the length of the boxes. N is equal to 1 over eta. So the dimension of line is then the log of n divided by the log of 1 over eta. It's the log of 1 over eta divided by the log of 1 over eta, it's 1. Okay? Getting more complicated, Cantor set. You start off with a line 1 unit long, so you need 1 box of size 1 to cover the whole thing. Second stage, you knock off the middle third, you now need 2 boxes, each of which is 1/3 of eta long. Do it again, you've got 4 boxes, each of which is 1/9 of eta long. You've got a pattern turning up there, and that pattern is that the number of boxes is going to be n squared, 2 squared, 2 raised to the power of n, whereas the length of the box is going to be 1/3 raised to the power of the level again. So the 0th is 1/3 to the 0, then you get 1/3 to the 1, there's 1/3 of the length is 1/3, 1/9, and so on and so forth. So the dimension of the Cantor set is going to be the log of n divided by the log of 1 over eta. That's the log of 2 raised to the power of n divided by the log of 1/3 raised to the power of n. That, again, is, you take the n's out the front, you've got the ratio of the 2 logs, it's 0.63. So the dimension of the Cantor set lies between 0 and 1. It's roughly 2/3. That's the idea of a fractal. Now, how the hell do we apply this to stock markets? Well, the idea behind fractals from Mandelbrot was measuring roughness, because if you look at the landscape, it's rough. If you look at a Euclidean object, it's smooth. Hold a smooth, like a table tennis ball in your hand, it's perfectly smooth. That means it's differentiable everywhere. Whereas, and therefore they have integer dimensions, whereas mountains, real-world objects, are rough. There's abrupt changes. You're walking along a mountain, you fall off a cliff. Okay? You're walking along a mountain, you walk into a cliff. They're very abrupt, sudden changes in the whole shape. You can't differentiate them everywhere. In fact, they're discontinuous everywhere. So the same sort of thing applies to the stock market. You can have big crashes, periods of smooth movements, and then very, very big crashes. So he said it's just like, in a sense, just like this Euclidean object, the non-Euclidean objects of the real world in geography, we find the stock market behaves the same way. So let's take a look at it. That's the data again for the Dow Jones in terms of daily movements in percentage terms from 1914 to 2009. And clearly, pretty rough, pretty jagged. What about the random data we looked at beforehand? This is that pseudo-random data using the same mean and same standard deviation. Now obviously it's more jagged than a sphere, but in a sense it smoothly fills the entire range of time. Notice too, by the way, the maximum upwards movement we're showing here is actually 20% movement in 1 day upwards is the maximum. It was actually, the biggest was actually 15% in 1 day, which was there. And the bottom down here is minus 30. The largest negative move was minus 22.6 in 1 day back in 1987. So it's pretty obvious they're different. But let's take a look at the box counting dimension and see how we go. So the first thing I've got to do is make them all boxes of 1 unit long. So I normalise them so that the maximum range, which is that 15% increase, is now 1 in the positive direction, and the minimum range, which is minus 22.6, is 0 at the other end of the box. So the box is 1 unit long, and the time period from 1959 to 2009 is also standardised to 1. Do that for the random data, that's what you get. Again, pretty obviously different. Now let's start dividing into boxes and see if the number of boxes versus the size of the boxes tells us anything. What you do is you count the number of squares that have got data in them. So if there's 4 squares, the need is now 0.5, and it's 4, the number of boxes that have got data are 4 in both cases. But if I then go to 16 squares, so it is now 0.25, all of a sudden there are some boxes in the real data that actually are blank. There's 13 boxes that have data, but there's 1 blank there, another blank there, and another blank there. What about the random data? All 16 are still filled. Now, if I keep on going from that stage from 4 to 16 to 64 squares, each time I'm halving, I'm squaring the number of squares, There's many, many more points now that are blank in the real data. Lots of them. You count them all, you find there's 34 blanks out of 64. So it's substantially different. Whereas the random are still, all 64 blocks are still filled. So there's something different. We're identifying them both very, very differently. Keep on going and write a program to do the whole thing, break into 8 squares, 8 by 8, then 16 by 16 and so on, and keep on going and going and going. And that's the program that does it. This is working again in MathCAD, a program I tend to use for most of my mathematical work. So that just goes through that same process I've shown you beforehand and tells you how many squares that have got data in them, and that's we're looking at the versus how many squares there are. And by the time I get down to an incredibly small square, 0.002 in size, there are 262,000 squares that could have data, but only 33,000 of them have data. Then I apply that rule and see what I get, and over time that rule converges to 1.67. So I'm saying the fractal dimension of the stock market is 1.67. What about the random data? Do the same process, and for a long time there's data in every square. Ultimately, you must get some places where the random distribution won't give you data, because you'll get some combination of a point in time where you don't get a really, really big movement up or down, and therefore those boxes are going to be blank. And that dimension sticks pretty much at 2. It falls below it because there have to be some blank entries. The more finely you divide the data, the less likely you are to get extreme data, which is where most of the blanks turn up with a random distribution. But that still sticks pretty close to 2. So that's telling a random process would give you a dimension of 2. What we actually see is a dimension of 1.67. Now, why does it matter? Well, again, there's no structure to a random process. If you throw 3 heads in a row, then the next throw of a coin has got a 50-50 chance of being head again, even though the chance of 4 in a row is only 6 out of 100. So the past history of the random tosses of a coin give you no idea of what the very next toss is going to be. But there is structure to a fractal process. There's some dynamic process explaining much of the movement, but not all, because there is some random stuff inside there. So you can actually say there's some way of using past information to derive information from the stock market. And that's, in some ways, there might be a lot of the chart stuff you'll see, the chart drawing stuff you'll see in the stock market is possibly capturing on a simplistic version of that. There are much more advanced versions I'll show you later. Now, of course, the process in the stock market isn't just isolated to the stock market itself. Of course, the stock market affects the real economies are affected by it, though maybe 2 or 3 orders of separation away. So there can be a pattern there, but it's incredibly hard to work it out. It may change. There may be many other factors beyond the stock market itself. But there's maybe enough information there to pull something out of it. Now, to show you why it's so hard, even if you exactly knew the equation that described the stock market's movements, it could still be incredibly hard to predict it. Of course, you can't know that equation. But there's one example I'll give you where you can know the equation, and still I'll show you how hard it is to work out what's going on. This is the logistic equation, as it's known. And it was used, not developed, but used to explain what happens when you see some animal populations, like, for example, red crabs or lemmings, where the populations tend to boom and bust in big ways at various times. But the key factor is they all give birth on the same day. This is a survival strategy, because you have huge numbers born on the one single day, relative to the overall population too. And that means that when they're born, the predators have an enormous feast, knock off lots of the ones that are born, but they can't eat all of them. So a few more go to survive and then get eaten the next day, and then ultimately a fraction of the total amount born each year do survive, so the population keeps on going. Now that gives you both a survival tactic, but also a tendency with population explosions and collapses, because if you have a large number of survivals in one year, then of course the population can exceed the carrying capacity of whatever resource that particular species depends upon. So if you're looking at red crabs, I don't know what they eat, but it might be seagrass. I think actually they're land-dwelling. Lemmings, I think they eat grass. They can then wipe out the resource they depend upon. And of course, the bigger the population itself is the fact that it makes it hard for the larger population to survive, because the death rate increases because they exhaust the food supply. So the logistic equation models this in about 4 different ways. First of all, it works in discrete time. T is the year of births. So it's saying the population this year is some function of population last year. And it's in discrete time, okay, because it suits a population where they're all born on one particular day. It wouldn't work for human population because we're born throughout the year, at different times, at the same days, etc., etc. You need a continuous function to handle that at the population level. Then there's a very high value for the A, which is the rate of reproduction per adult. So that means there are lots of children per adult up here. And then the B factor is negative, and it tells you that each additional animal negatively impacts the survival possibility of other animals by eating the resources that are available. So that's the basic way the equation works. And you can also express it in this form, which reduces it to its factors. Now, it's a toy model, but it's realistic to some degree, and it's completely deterministic. There's no random noise in this one. But it behaves chaotically for some values of A and B. So let's take a look at that. And it's called, these ideas were first worked out, they were called chaos. And now more commonly called complex systems. But they're used to describe systems which are deterministic. Okay, there's noise in there as well, but a core part of the behaviour is a process that depends upon past values of the system. But they're highly unstable and end up being unpredictable even though you might know the equation that describes them. Now, lemmings are a good example of that. So this is a little simulation that's saying, let's say we know the number of lemmings at a particular time, and we want to simulate how many there are over time, and we know what the equilibrium would be given that equation. Okay, here we go for our simulation. The green line is the equilibrium. The red line is the actual population at different breeding seasons. Now, knowing the equilibrium doesn't tell you what's going to happen. Okay? One of those classic instances where you've got to go beyond just thinking in terms of the equilibrium to look at the cycles that occur to see what the hell's happening. So even if you knew that that was going to be the equilibrium, you couldn't use it to say what the value is going to be in any particular year. And as I'll show you in a moment, even if you almost precisely know the value in a particular year, within a short period ahead, you can't work out what's going to happen. So you also, for some values of A, get a stable population. So if I make that population growth rate lower, let's just zoom this down a bit, and make the population growth rate under 2, say 1.4 per adult, then what you get is a very rapid convergence to a lower equilibrium. But if you have a value of 2, for example, or slightly over 2, what you get is what mathematicians call a 2 cycle. So you bounce between two values indefinitely. The equilibrium's in the middle, you never get there, you bounce one side to the other. You can imagine what's going on. You have slightly more born than the ecosystem can carry, so there are more deaths. They fall below the level that it can carry, so there are more that survive, and you bounce up and down. And mathematicians refer to the equilibrium that economists think applies everywhere as a 1 cycle, meaning you cycle from one value to another value through time. So there's nothing special about equilibrium in this way of looking at the world. So there's your 2 cycle. Now, if you go up to a slightly higher population growth level, you get a 4 cycle. So I try 2.5 there. I'll just cut rid of the overplots there as well. Run it again. You now get 4 values that repeat indefinitely. And if I make it higher again, at some point you'll get 8. That might well be the 8th cycle going on there. Keep on going past that level, however. Yes, I got past here, that's about the 8 level. Now it doesn't go 16, yeah.
Actually, if you really see, in economics literature, sometimes they call this as multiple equilibrium.
Multiple equilibrium.
Multiple, more than one.
Yeah, but it's not an equilibrium.
In the sense that there is switching happening between different states.
I think it's still a abuse of the word equilibrium. Equilibrium means you tend towards that value, or there's an equilibrium there, but it's a single equilibrium. If I go up to a higher value for, let's say take it past the chaotic point, just make a point to the class here. I went from 2 cycle to 4 cycle to 8 cycle to 16 cycle. If you keep on going, you don't just keep on getting higher and higher integer values, you pass through discontinuity. Past a certain point you get through infinite cycles, and then you go on the other side of infinite, and what you get then is what we first called chaos. And I'll show you that quickly on the slide here, and then illustrate it using VisSim as well. That's a chaotic pattern. Now, why I'm objecting to saying it's an equilibrium or multiple equilibrium, no value is ever repeated in that sequence.
No, but if you plot the histogram, right, there will be 2 peaks or 3 peaks or 4 peaks. If you draw the histogram, suppose
Yeah.
there are 2 cycles,
Yeah,
and if you draw the PDF of a histogram,
yeah.
you will see 2 peaks.
Yeah, but what you're doing is you're losing information. And if I go past a certain point again, I can go through other bifurcations. So, I mean, to me, it's an abuse of English. Economists are extremely good at abusing the English language. Okay, I think the English language has got a definite case of rape when it comes to what economists have done to it, and that's another instance of the same thing. So, you know, it is not a multiple equilibria, because once you get past 2.73, there is no equilibrium. There is an equilibrium, but you'll never be there. Okay, so I would define the equilibrium as the green line. I define the points that it goes through as a disequilibrium process. That's actually where the data ends up being. Now, so no number ever repeats itself, and even though you know the model precisely, and this is the interesting part of what I'm arguing here in terms of whether you could use the same ideas for the stock market, the smallest error you make in what you think you know about the system gets blown out over time. So let's say you get the population wrong by 1%, which is pretty accurate. Economists would be happy to be 99% right about the value of any economic variable. Well, after very few cycles, your estimate's completely wrong. You notice just down here, the prediction is accurate. The bottom plot shows the gap between what you think you've got and how many you have got, and it's a pretty small gap for the first 10 cycles. But after a while, it's a huge gap, and there's no pattern to it at all. Let's watch that one. Pardon me. Bring up the bottom chart here. Again, I've embedded this in the presentation so you can take a look yourselves on the demo version of VisSim. So the bottom one shows you the percentage you're wrong, ranging between plus 99% virtually and minus 280% wrong in your guess as to how many actual lemmings you have in that system. So there's many instances like that, and one is the stock market. And that is, you've got a current value which to some degree depends upon previous values, unlike a random process, but it's such a non-linear process, there's the 2 examples there from Logistic and Lorenz, that the pattern is almost but not quite unpredictable. Now, behind that pattern is what chaos theory and complexity theory people have named self-similarity. And I'm going to take you through a bit of this as well and then see how that also applies to the stock market. But probably the most early and beautiful example of this was developed by Mandelbrot himself. It's known as the Mandelbrot Set, plot after him. And it's rather nice to have something as spectacular as that named after you for posterity. That's the Mandelbrot plot. Anybody ever seen it before in the class? A few, okay. Now, if you zoom in on a part of that, what looks like the whole is going to appear there. That's a slice by slice, so taking a small slice out of it in the upper left-hand corner there, and then blowing that up, that's what you get. Then take that small bit and blow it up, that's what you get, and keep on diving down, and you can see the overall shape that I showed you turns up a couple of times. You keep on doing, you'll find it again. Here's a little movie to illustrate the same thing. That's zooming in obviously part of that overall shape, and as you zoom in, an absolutely tiny scale, you once again see the same shape, and zoom into what appears blank initially. The same thing turns up again. So looking at this, if you've shown an illustration from it, you wouldn't actually know what scale you were looking at. Were you looking at the entire plot, or were you looking at a tiny fraction of it? Okay. Without some very sophisticated knowledge of what you were looking at, you wouldn't be able to answer the question. And maybe even with that knowledge, you couldn't answer the question. So that's the Mandelbrot plot.
Steve, does it matter how deep you look in? Because if you go out, it's going to be the same story, right?
Yeah, at a certain point, I believe, I've forgotten the details here, but I believe that it stops at any number which has a modulus of less than 1, the initial starting point. Okay, so at a certain point, your region is predefined, but then within that, you get those incredible patterns. I've got to check that. Take a look and find out for me. I'd like to check that one out. It's a long time since I've looked at the actual mathematics of the proper definition. I believe it's they have to have a modulus of less than 1 to start with. Now, what's actually going on there? You'd imagine something that complicated would require an incredibly complicated rule to generate it. That's so showing it. To me, it looks like some illustration from Hindu mythology. Okay, all it is you take a number, square it, add a constant, and use the new number for an input to the next one if the magnitude of the old one exceeds 2. Otherwise, you stop. Now, there's only one complication to that, and that is Z and C are both what are called complex numbers, where they can be defined as in x plus I times y, where x and y are both real numbers, and I is the square root of -1. Now, who in the room has ever seen the square root, that expression before, the square root of -1? Again, our engineers. Anybody else in the class? Okie dokie. That's the sort of mathematics you should be taught, because what you're looking at, when you're looking at the economy, is a complex, fluctuating system. It ain't in equilibrium. And the mathematics you need to handle fluctuating systems fundamentally involves complex numbers. Engineers learn it, as you can see from our reps in the front row. For example, the electricity in this room, the equations to define how that behaves inherently have complex numbers in them. So it's a sign that you're not being taught the right mathematics. You haven't ever even seen them before. Now, the way they're represented by mathematicians and engineers is by taking the idea of the number line we use for real numbers and then drawing in another one where the numbers are real but multiplied by the square root of -1. So there's your normal number line from -infinity to +infinity. Complex numbers you represent on the vertical axis and say they're -infinity to +infinity times the square root of -1. And Mandelbrot function says take some number down here somewhere and apply that operation to it. Square it, add a constant, work out its magnitude. If the magnitude is greater than 2, keep on going. And the magnitude you can represent it either as the height above the xy plane or the distance from the origin on that plot there. And then you show what the distance is or what the height is using colours. Now what you get is the black bits are where the height's 0, the colour bits are where the height's greater than 0, and that's the sort of pattern you... Again, looks amazing. But in 3D, that's more what it looks like an incredibly complicated mountain in the middle area there. And if you look on side on, it reminds me of the cathedral, that's the Gaudi cathedral that's being built in Barcelona, and maybe in 75 years will be finished. Dramatically, incredibly beautiful structure. Now, the main relevance of all this to what I'm talking about in finance is that you can get unpredictable behaviour from actually quite simple rules. And yet the data itself will be self-similar. You will have the same sort of crashes occurring on a daily basis that you have over the very long term. And you can find a pattern behind all that stuff, but it'll be a highly complex nonlinear pattern subject to other influences as well. So there is information to be found in there. You may be able to make money out of it, but it's a highly difficult thing, even if you know the system you're working with. And let's go on from there after that, after the break. Take about 15 minutes or so.